let's begin with our quantum field theory lecture. Some more participants, very good. So yesterday we ended up with calculating the photon vacuum polarization in quantum electrodynamics. And we went through a sequence of calculational tricks which are maybe mostly unfamiliar to you, and so we did it very quickly. We had the idea of dimensional regularization, where integrals are defined in d dimensions. We derived the so-called master formula for one-loop integrals. We derived the formula for the B0 function with certain simple arguments. And for the photon vacuum polarization, I showed you two very general tricks: Feynman parametrization and integration by parts. And combining all of those methods, we arrived at this extremely simple formula for the photon vacuum polarization. And now we want to discuss what it means. First of all, we will analyze the formula itself by looking at some limits in order to get some insight what the formula actually tells us, and then we will do physics interpretation of the photon vacuum polarization. So let us begin with studying some limits. And in order to evaluate the limits, let's first look at some integrals. For example, the combination which appears here a few times in the formula is this integral from 0 to 1 dx x minus x squared. And so we need to integrate polynomials. X squared from 0 to 1 gives 1/2. X integrated from 0 to 1 gives 1/2, x squared gives minus 1/3, and so the overall result is 1/6. And then what we also need is the B0 function. That was evaluated to this divergent combination capital delta plus a logarithm integrated over 0 to 1 logarithm of mu squared divided by q integrated over x. And q is an abbreviation for a polynomial in x, which also depends on the physical variables m squared and q squared. Okay, so then we have enough so that we can compute our photon vacuum polarization, and I will write down the results for the combination A gamma, where we have factored out the coupling constants, so to extract really the functional dependence on the mass and the momentum. So let us first look at the divergent part. The divergent part of this A gamma comes from plugging in the divergent part into the B0 function, and the finite part comes from taking the finite part of the B0 function. So first the divergent part, A gamma divergent of q square is what? So then we have the 1/16 pi square times 8 times the integral over the combination here times the divergent part of B0, which is just delta. So delta is just one factor, and all the prefactors come from 8 divided by 16 divided by 6 is 1/12. 1/12 pi square times delta. That is the result, and interestingly, the result is independent of the momentum q square. So what is really noteworthy is the result here is a momentum independent constant. We will come back to this insight. The divergence is not depending on the momentum. Then let us look at the finite part. And as a first example, let us evaluate the finite part for the specific momentum 0, q square equals 0 in the argument. What happens if we evaluate the B0 function at q square equals 0? If small q square is 0, the big Q is just m square. Big Q is just m square, so here we have mu square divided by m square. that doesn't depend on x. So the integral from 0 to 1 gives just the argument. So we get ln mu squared over m squared. So we have ln mu squared over m squared times the same prefactor, so we get 1 over 12 pi squared times ln mu squared over m squared. So that is just a constant. This is the finite part at 0 momentum, and it's some constant which depends on the mass and which depends on this unphysical mass scale mu. Then we can, for all the other q square, let us use again another split. Let's write the finite part for an arbitrary q square as the finite part at 0 plus a rest. Okay, let's split off the 0 contribution plus a rest, and the rest I call here a hat gamma, finite of q square. So a hat of q square is just the original a minus a at 0. And maybe to make it even more explicit, let me write down the full a gamma. The full a gamma of q square is now the following. It's first of all the divergent part, which is a momentum independent constant as we saw, plus the finite part at 0 plus the a hat finite at q square. So this is now the way how we split our a gamma into 3 contributions: divergent, finite at 0, and a rest. And the rest is then of course the interesting thing which gives us the physical dependence on q square. So therefore let us evaluate this finite remainder, a hat finite of q square. This is now the following. So the prefactor is 1 over 2 pi square times the following integral. 1 over 2 pi square times the following integral from 0 to 1 dx, and the integrand is x minus x square times now the part from the b0 function where we put in the full capital Q, but we have subtracted away this part here. So subtracting off that logarithm from this logarithm means nothing else but replacing the mu square by m square. So the difference between the two logs, the ln mu square cancels, and you get an ln m square in the numerator. So therefore we have here the following integrand: ln m square divided by m square minus q square times x minus x square. And that now really extracts the physical part, the interesting part of the vacuum polarization, as an explicit integral. That is still a non-trivial integral, but it's also not too complicated and it can be evaluated. Yeah. Ah, that's right. Yeah, that relative sign is definitely correct. I don't know what we had yesterday, but I'm absolutely sure that this sign is correct. That was your second remark. So what you can memorize and what I know is that the relative sign between the divergence delta and the ln mu square is always positive. So you can see this from the derivation that actually we started with mu squared to the power epsilon times gamma of epsilon. So this combination is what always appears in from the structure of dimensional regularization, and therefore if this is replaced by 1 over epsilon, you inevitably get 1 over epsilon plus ln mu square. So this relative sign is completely fixed right from the beginning. Therefore the sign is definitely correct. And it is also something that you can memorize. It's often important to see that correlation. Okay, but here we now have an explicit formula for the finite remainder, which is a complicated function of q square, but we can now evaluate it. We can of course evaluate the integral analytically using some mathematics, but let's not do that. Let's look at some special cases which are physically interesting. One interesting case is the limit q square going to 0, where we can do a Taylor expansion in q square. If we have small q square, then the logarithm here in the integral can be first of all written as ln 1 divided by 1 minus q square over m square times x minus x square. Okay, this is still exact. But then q square over m square is regarded as a very small quantity, and we do a Taylor expansion in this small quantity. It is differentiable at q square equals 0. There is no singularity at all, so Taylor expansion works completely fine. And the Taylor expansion of logarithm of 1 plus x is simply x. So therefore we get here simply q square over m square times x minus x square. That's simply the first order Taylor expansion. And then we can plug in this Taylor expanded log into the integral, and then the integral becomes just an integral over a polynomial in x instead of a combination of polynomial and log. So then we get the following integral. Just looking at the integral only, we get x minus x square from here and another x minus x square from there, so we get x minus x square squared, which is the integral of x square minus 2x cubed plus x to the fourth. Okay. So this integral can of course be evaluated. The integral of x square is 1 over 3. Integral of x cubed is minus 2 over 4, and x to the 4 gives 1 over 5. So then you have to add those numbers. So the common denominator is 30. So here you have 10 over 30 minus 15 over 30 plus 6 over 30 gives overall 1 over 30. Then plugging that in completely, then we have evaluated the integral over the log. We have in addition the prefactor q square over m square and that here. So therefore we have a gamma hat finite of very small q square is approximately 1 over 6t pi square times q square over m square. And what we have neglected is terms of the order q to the 4. So we have done a Taylor expansion around q square equals 0. So the result is Taylor expandable, and the first order looks like that. So that is nice, and we will use it for physics discussions later on. Then a last limit, q square going to infinity. Let's look at the magnitude of q square going to infinity. So we can have both positive q square or negative q square, because it's a Minkowski 4 momentum, which could be a T-channel in a Feynman diagram or an S-channel in a Feynman diagram. So let's look at both cases, and then what we do in the log is simply we neglect the mass entirely. So this mass is neglected entirely, and then the log becomes approximately ln m square over minus q square plus the log of 1 over x minus x square. So a log of a product gives the sum of the individual logs, right? And so I separated off the log here, which is x dependent, and the log which is non-x dependent. And I've neglected the mass entirely. Therefore that becomes a product. So here we have a dimensionless physics ratio, and here we have a dimensionless ratio just from numbers, which is easy to integrate, but actually we don't even care about it, because that is interesting because it's logarithmically enhanced. So for very large momenta, this goes to infinity, and becomes dominant, whereas that is not depending on the physics variables, it's independent of q square, therefore that remains a constant. And so for very large q square we need to take into account only that, and we will neglect everything else. Therefore for very large q square the log is approximately just given by this, and then we get the prefactor that we already know from the integral, which is 1/6 times that. And so therefore we can write approximately q square going to infinity is approximately 1/12 pi square times logarithm of m square divided by minus q square, and what we have neglected are non-log enhanced terms. So here at infinity the result has no Taylor expansion, but it's logarithmically divergent, and that is also interesting for the physics interpretation later on. So, and I want to highlight this once more, and we will discuss it in more detail later. But this is a typical behavior, and therefore I wanted to look at all these limits as opposed to doing an exact calculation, but the limits give you some insight. It is very typical that at low energies you can do a Taylor expansion of such results, whereas at high energies you typically get a logarithmic enhancement, which is really a new effect from the quantum theory and from the higher order effects, because at T level you see that looking at the Feynman diagrams there is absolutely no way you could get a logarithmic energy dependence, but due to those higher orders you get such dependencies, and so this is one of the new quantum effects.
طبعا الديبندنس energetic dependence ولا الطاقة، الاعتماد على الطاقة، أيضا ذهبت إليه نظريتي في موضوع الكواركات، حيث أنه عميقا داخل البروتون حيث الجاذبية عالية فإن الكتلة تصغر والطاقة تكبر. هذا طبعا ما توصل إليه هذا البروفيسور في هذه النظرية، أن الطاقة تكبر. هو طبعا افترضها افتراضا، لكن أعطته نتائج جميلة جدا في المعادلة، أن الطاقة تكبر والكتلة تصغر. ما الذي يؤدي الكتلة أن تصغر؟ شيء بسيط وسهل حسب كتاب الحلقة 54، ويؤدي الكتلة أنها تصغر حيث أنه أن الفضاء يستعيد التناظر له تحت الجاذبية. هو مفترض يكون العكس، أنا ما أعرف لماذا وصلت لهذه المعلومة، مفترض يكون العكس. نعم نعم الفضاء يستعيد الجاذبية، يستعيد لا يختلف، الفضاء تختلف فيه يزيد الاختلاف في يزيد الاختلاف في السيمتري، وهذا ما يعطينا زيادة الكتلة. لكن نجد أن البي اللي هو المجال المغناطيسي يضعف مع زيادة الكيرفيتشر، لا هو مفترض يزيد مع زيادة الكيرفيتشر. عموما سأراجع هذا الأمر في كتاب الحلقة 54، لأنه مفترض مع زيادة الجاذبية مفترض أنه كتلة تتضخم ولا تصغر. ما الذي جعلها يصغر؟ تبادل الأبعاد. أعتقد أن تبادل الأبعاد هو السبب، يعني جعل الكتلة تصغر، على ما أعتقد هذا. سأراجع هذا الأمر.
So let us then look at the interpretation of all of this. that is section 5.3, the physics of the photon vacuum polarization. All right, let us start with the QED 3 level predictions. Headline 531. Let's first look at some observables. So 531 is observables. And let us, in order to define observables in a simple way, look at some tree-level processes. For example, here Compton scattering, or E plus E minus to mu plus mu minus, and so on. Different angles, different energies, and of course there could be more processes. But if you predict these processes at tree level, you will always find the result of the following structure. Namely, we always get some cross-section d sigma by d omega, which is proportional to alpha divided by some momentum q square from these internal propagators. And so that would be the Feynman diagram, and the Feynman diagram is squared. So we get something like alpha over some momentum squared, overall squared, times some other function of the energy and angles and so on. Okay, so this is always the structure where alpha is given by the coupling constant E square over 4 pi, and I just write alpha because this is a common abbreviation for this combination here. Okay, so all these three-level processes will have a formula that looks like this. And now what we can do is we can define something that we can call pseudo-observables, which are not directly real observables in experiment, but it's possible for experimentalists to translate their findings into such pseudo-observables which are easy to compare to theory. And so for our lecture purposes, that would be a very good thing to look at. So in experiments, we can define something like a pseudo-observable. And of course, not all observables will be brought into that form, but just for
موضوع السودو observable فقط أنا أريدكم أن تعتبروا حسب نظريتي أن هؤلاء الملاحظين أو الأشياء الملاحظة اللي هو الobservable هذه قد يكون أحدها هو أن يكون الملاحظ قريب جدا من هذا التفاعل، وبالتالي سيرى الكتل غير متفقة، سيراها مختلفة، وسيرى فيزياء مختلفة. لكن في النهاية هذه الفيزياء ستوصل إلى الفيزياء القياسات التي الobservable أو الobserver الموجودين في الخارج، يعني كأنه حلقة وصل بين الفيزياء الحقيقية الموجودة داخل هذه التفاعلات وما يشاهده الملاحظون الموجودون في الخارج. هو سيكون حلقة وصل، يعني ممكن يبنوا عليها. لكن أريدكم تلاحظوا أن ما سيقوله هنا عن السودو observable يتم تطبيقه على الملاحظين الموجودين قريبين من هذه التفاعلات، وكيف يرون هذه الفيزياء. فهي ليست السودو بالنسبة لنا السودو، لكن هي ليست السودو، وبالحقيقة ليس السودو نهائيا، ليس السودو إنما هي حقيقية. لكن نحن أو الميكانيكا الكم لا تعترف بالتغيرات التي تحصل في الفيزياء بالنسبة للتغيرات التي تحصل في الجاذبية، لهذا يعتبرونها السودو، لكن هي ليست السودو، هي حقيقية.
Pedagogical purposes, let's look at such observables where we can write that the experimentally observed cross-section, the sigma by the omega, which directly comes from data, let's say experiment I, we have many experiments labeled by an index I, they can be mapped to the tree-level QED prediction by definition. So you just basically divide your experimental result divided by the tree-level QED prediction, and you see that QED prediction depends on alpha square, and then you can define what we call an effective alpha for the experiment I. So what that means is that you take the tree-level formula and you replace the theory alpha by some new quantity, and that new quantity defines your measurement, right? You can always write your measurement in the form of tree-level prediction with some value of alpha. For some value of alpha, the tree-level prediction matches your measurement, and therefore by construction you can call that alpha the observable from your experiment, and so then you have.
بالمناسبة هذا الأمر دونته في كتابي من قبل أن أشاهد المحاضرة. في الحقيقة أنا المحاضرة 24 هذه لم أشاهدها، أو هذه اللقطة لم أشاهدها. أنا في المراجعة الأولى أو في المسح السطحي وصلت إلى أجزاء معينة في محاضرة 24 وتوقفت، وبعد ذلك عدت السلسلة مرة أخرى بالتسجيل. فهذه قد أكون مررت بها لكن لا أفقه شيئا عنها الآن، يعني كأنها أول مرة أمر بها. والغريب أنا دونت ذلك في كتابي الحلقة 54 الذي سيخرج إن شاء الله خلال اليوم أو بكرة بإذن الله تعالى. دونت ذلك لأنه حسب نظرية سيرياك طبعا عملت تعديل عليها، يعني الكتب 36 و37 38 و39 عملت تعديل عليها. التعديل ليس اختلافا كثيرا، إنما شيء أكثر ضبطا. هذا التعديل تعني بنتائج ليست مذكورة في هذه الكتب، وفسرت هذه النتائج بالضبط بعملية القسمة هذه، بالضبط بعملية القسمة هذه. فعندما كتبت قلت أن بالنسبة لمتجهات الوحدة خارج الفضاء وداخل الفضاء تختلف، وهذا الاختلاف يعني خارج الفضاء فضاء التفاعل، وداخل الفضاء هو فضاء التفاعل. هذا الاختلاف يجعل ويوحي كأن الفضاء غير متصل، لكن في الحقيقة الفضاء متصل. بما أن الفضاء متصل فإننا ما سنفعله هو قسمة أو إيجاد رابط، أنا كتبت هكذا، إيجاد رابط بين ما نراه في الفضاء الداخلي على ما نراه في الفضاء الخارجي. وهذا طبعا بسبب هذا الاختلاف جاء بسبب أن البروتون ليس كتلته ليست واحدة. في هذا الأمر إن يعني مستحيل فيزياء تعرف هذا الموضوع ما عدا في فيزياء واحدة هي فيزياء كيبلر. كيبلر أدرك هذا الموضوع عن طريق القانون الثالث لحركة الكواكب، حيث أن مربع الزمن الدوري أو مكعب النصف القطر الذي يقطع مساحات مساوية في أزمنة مساوية، فإن مكعب مربع الزمن الدوري على مكعب نصف القطر يكون ثابتا. هذا الأمر إذا تم تعويضه، طبعا ثابت التناسب عبارة عن ثابت نيوتن مضروبة في الكتلة. ثابت التناسب هذا يتغير بتغير الاختلاف بين مربع الزمن ومكعب المسافة. بالمناسبة مربع الزمن ومكعب المسافة يختلفان وليس ثابتا، وهذا واضح إذا حاول أن تعوض مربع المسافة أو حاول أن تعوض هذه الكميات اللي هو مربع السرعة على مكعب المسافة بدلالة المسافة والسرعة. يعني أقلب الموضوع ستبقى R تكعيب على T تربيع، R تكعيب على T تربيع تساوي R في C تربيع، اللي هو R في V اللي هو R المسافة و V تربيع هي السرعة، والطرف الآخر ستكون هناك 2 أو 4 على جي ام، جي ثابت نيوتن وام الكتلة. طيب هذه النسبة تعطينا تغير في الكتلة أو تغير في ثابت نيوتن أحدهما. إذا افترضت تغير في الكتلة يمشي، إذا افترضت تغير ثابت نيوتن أيضا يمشي. فهذا التغير لا هو الار تكعيب في تي تربيع لن يعطينا الار تكعيب في يعطينا الكتلة في مضروبة في ثابت نيوتن ليست مقسومة على ما أظن، لأنه عدد كبير ار في في تربيع عدد كبير لما تقسم على ثابت نيوتن يعطينا الكتلة. هذا التغير في الكتلة يتوافق مع يعني زيادة نصف القطر، يتوافق مع نقصان زيادة الكتلة، ومرسلة يتوافق مع نقصان الكتلة. نعم يعطينا مقلوب نعم مقلوب الكتلة، و على ما أظن ذلك يمكنكم المراجعة. المهم فمن استخلصت أنا في كتبي الحلقة 41 و 42 و 43 أن الاختلاف في نصف القطر اللي هو نصف قطر الدوران قادم من الاختلاف في كتلة الشمس بالنسبة للملاحظ الموجود. يعني الأرض ترى كتلة الشمس مختلفة عن نبتون أو مختلفة عن المريخ أو بلوتو لكتلة الأرض. هذا الاختلاف ناتج عن الملاحظ. بالتالي هذا يطبق أيضا في التفاعلات الداخلية، بحيث أنه الملاحظ الموجود في الخارج بعيدا لا يرى طاقات ضعيفة جدا أو يرى تغيرات في الكتلة، وهو لا يعلم من أين جاءت هذه التغيرات في الكتلة، لكن في الحقيقة هي جاءت من هذه الفيزياء المختلفة. فبقسمة الملاحظ القريب إلى الملاحظ البعيد تعطينا هذا الاختلاف. يعني يمكن أن نبني نظرية عن الملاحظ القريب عن الملاحظ البعيد بدلالة الملاحظ القريب. ستجدون هذا الأمر واضحا في كتاب إن شاء الله الحلقة 54.
A very simple way to communicate your result and compare the results of different experiments and also compare with theory. And of course, that is a more theoretical way to look at experiments, but it's very useful for our lecture. So every experimental result could be communicated by, in this way, by defining an effective alpha. And so then, let's say, each observable defines an effective alpha, effective for experiment I. And what we have learned from before, the QED tree-level prediction. QED tree-level prediction exists, and the QED tree-level prediction would of course be by construction that all of those effective alphas are predicted to be the theory alpha. That is the construction recipe. So for each experiment, the QED prediction would be the same. At tree level, you predict that the effective alpha is equal to the theory alpha. And in particular, the QED tree level prediction is that all of those experimentally measured effective alphas are all the same. That is simply by construction, in order basically to bring all the experiments onto an equal footing and to make it easy to analyze from the theory point of view what now happens at higher orders, because at higher orders QED does not predict that all the effective alphas will be the same, but at higher orders QED will predict something more complicated, and that is however now very easy to compare and analyze. So what we get in QED at higher orders is the following. So in QED at higher orders we will have new Feynman diagrams, and in particular we have done the approximation where the only higher order Feynman diagrams are in the photon vacuum polarization. So therefore such processes will get a correction from the photon vacuum polarization. And so then basically what happens is that instead of E square divided by Q square at 3 level, we now have E square divided by Q square times 1 plus pi gamma of Q square. That is the new prediction, right? That is what we have seen. And so here I put the version of the one loop correction with this resummed vacuum polarization, which went into the denominator because we have summed a geometric series. One could also write in the numerator times 1 minus pi gamma. At the one loop level it's the same. Okay, so that is the prediction. And now comparing this to our experimental definition of the effective alphas, it simply means that at higher orders QED in our approximation predicts now the following, namely the effective alpha of experiment I, which works at some particular Q square, is now given by, instead of this, by this expression, and the difference is the factor in the denominator 1 plus pi gamma. So we have E square divided by 4 pi divided by 1 plus pi gamma of Q square, where the Q square is the Q square which is relevant for the experiment number I. That is the prediction at higher orders. And so you see that at higher orders QED does not anymore predict that all the effective alphas would be the same, but each experiment gets a higher order correction in the predicted version, and this higher order correction depends on the vacuum polarization, where we insert the momentum which is relevant for the process that we consider. And so therefore we instead of E square divided by Q square at 3 level, we now have E square divided by Q square times 1 plus pi gamma of Q square. That is the new prediction, right? That is what we have seen. And so here I put the version of the one loop correction with this resummed vacuum polarization, which went into the denominator because we have summed a geometric series. One could also write in the numerator times 1 minus pi gamma. At the one loop level it's the same. Okay, so that is the prediction. And now comparing this to our experimental definition of the effective alphas, it simply means that at higher orders QED in our approximation predicts now the following, namely the effective alpha of experiment I, which works at some particular Q square, is now given by, instead of this, by this expression, and the difference is the factor in the denominator 1 plus pi gamma. So we have E square divided by 4 pi divided by 1 plus pi gamma of Q square, where the Q square is the Q square which is relevant for the experiment number I. That is the prediction at higher orders. And so you see that at higher orders QED does not anymore predict that all the effective alphas would be the same, but each experiment gets a higher order correction in the predicted version, and this higher order correction depends on the vacuum polarization, where we insert the momentum which is relevant for the process that we consider. And so therefore we can then basically come back to our sketch that we had yesterday. So we have this parameter in QED E, and as a function of this parameter we calculate predictions for all interesting observables. So for example, we predict here the observable E plus E minus at low energies. That would be observable 1, and then we might get alpha effective in the Thomson limit would be predicted to be E square over 4 pi divided by 1 plus E square times this A gamma of, sorry, little bit not enough space, E square times A gamma of 0, right? So Thomson limit for some scattering processes works at 0 momentum. That was the definition of Thomson limit, and therefore we get evaluated the photon vacuum polarization at 0 momentum. So and then we can write this as an effective alpha in the Thomson limit is given by that combination. Then another experiment at high energies, let's say alpha effective high energy would be given by E square over 4 pi divided by 1 plus E square A gamma of Q square at some high value. And so on. Okay, so you can now write down many observables like this, and you see the structure from yesterday has emerged. We have one input parameter E, and as a function of that we can predict infinitely many observables. I wrote down 2 here, encapsulated in terms of this effective alpha, where the formulas are very simple and transparent, hopefully.
طبعا انظر إلى كلامه هذا في غاية الدقة واتفاق كامل مع نظريتي. وذكر أن في هذه المعادلات ترى أن الإي طبعا تعتبر الشحنة إي سكوير تنقص مع الهاي انرجيز، وهذا واضح أن نجد أن الهاي انرجيز بالنسبة للتفاعلات المادية تعطينا مسافات أقل. هذه المسافات أقل تحدد شكل الجسيمات الموجودة هناك. يعني مثلا لدينا البروتون لديه كواركات لديه كتل أقل بسبب المسافات الأقل، لكن طاقتها عالية. طيب هذه الطاقة العالية، طبعا هذه الطاقة العالية تظهر في تماسك الخواص المغناطيسية، حيث أن الخواص المغناطيسية تعمل على تماسك هذه الجسيمات بقوة أكبر، كما سنكتشف ذلك من خلال كتابي القادم. هذه الطاقة العالية يتبعها ماذا؟ نقصان في الشحنة ونقصان في الكتلة. نحن نعلم أن كتلة الكواركات صغيرة، يعني الكوارك مجموعة 3 كواركات داخل البروتون والنيوترون لا تفوت 10 ميجا، وكتلة البروتون والنيوترون 1 جيجا. إذن ليست وحدها الكواركات التي ليست كتل الكواركات التي تؤدي إلى تماسك البروتون. أيضا الطاقة المفترض أن تؤدي إلى تبعثر البروتون وليس تماسك البروتون، لأنها طاقة عالية جدا، المفترض أن تؤدي إلى تبعثر البروتون. لكن دعونا نلتزم الآن بأنه الطاقة طبعا الطاقة هي المغناطيس التي تؤدي إلى تماسك البروتون، لكن دعونا نقول أن الطاقة أيضا اللي هو تظهر في شكل جلونات هي التي تؤدي إلى تماسك البروتون. هنا يحصل أن كتلة الكوارك صغيرة، شحنة الكوارك صغيرة، أيضا الشحنة يحصل فيها كسر، تكون الشحنة ذاتها صغيرة. وهنا ما شرحها هذا المحاضر وهو إذا زاد المقام غلى البسط والبسط موجود فيه الشحنة. طبعا موجود مفترض يكون موجود شيء أو معادلة أخرى تعبر عن الكتلة، بالتالي زيادة الطاقة للكوارك يؤدي إلى نقصان الشحنة والكتلة. هذا مفترض أن يحصل في التفاعلات النووية أو التفاعلات الدقيقة. أما هذه الكواركات إذا خرج البروتون فإن هذه الكواركات تتضخم ولديها أحد سلوكين، إما أن تتضخم تصبح مثل التوب كوارك والبوتوم كوارك. توب 172 جيجا، البوتوم 4 جيجا، عندك الشارم 1 و200 جيجا، كلها أكبر من البروتون والنيوترون. أو أن تفعل كالآتي، أن تستطيع الكوارك أو يستطيع الفضاء الصغير الأبعاد أن يحجم هذا التضخم بالكوارك بحيث أنه يلصقه بالإذبن أو النقيض له في الأيس إذبن، وبالتالي نجد أن الكوارك يجر معه أنتي كوارك مباشرة. حتى الكواركات الضخمة تجر مع أنتي كوارك، فالكوارك يجر معه أنتي كوارك. هذا من أجل أنه لا سرعة طاقته لا تكون عالية، كتلته لا تكون عالية. ونجد أن الكواركات الضخمة تتحلل بسرعة، لأن الفضاء ثانوي الأبعاد لا يحتمل وجودها إلا أن تقود معها أنتي كوارك، لا يحتمل وجودها كله نهائيا، فتتحلل بسرعة. التوب كوارك يتحلل بسرعة، البروتون يتحلل بسرعة، وهكذا. أكثر كواركات ثابتة هي كواركات الجيل الأول التي تعتبر الأب داون، هي أكثر كواركات ثابتة وتظهر في البروتونات في الباريونات وتظهر في الميزونات الأب داون، ثم السترينج، بعد ذلك يظهر في عديد من الميزونات، بعد ذلك يظهر البوتوم على ما أظن، وهكذا. فإذا هذه المعادلة دقيقة وتتفق تماما مع نظريتي.
And so now we can discuss on the one hand the so-called renormalization scheme, where the divergences drop out, and we will see how they drop out and why they universally drop out for all observables simultaneously, because that was a non-trivial hope from yesterday, and we will see that it is fulfilled. And the next thing is that we will actually discuss the physics in implications, because we see here already something interesting happens both at low energies and at high energies, and therefore there will be interesting predictions from the QED higher orders for low energy and for high energy processes. So our next section is indeed renormalization. And we will explain renormalization with the help of this particular example here, and that is quite sufficient to show you the general principles in line with our ideas that we developed yesterday. So the general procedure of renormalization in practice can be basically divided into 5 steps that you need to take. And of course here it's a little bit overkill probably, but I will nevertheless go through all of these 5 steps, which can be applied in the same way also for very complicated cases like the electroweak standard model, where all the steps are very involved, but the steps are the same. And so therefore let me do it. Here most steps are actually trivial. So step 1. Step 1 is the so-called renormalization transformation. We have now seen and established that our parameter E is not an observable, but it is a formal theory parameter as a function of which we can compute observables, but the relationship between E and observables might actually be divergent, and so E itself is unphysical. And we have already introduced the name bare quantities for such unphysical objects, and so let us now make this more explicit by relabeling it. So the E so far will now be called really E bare with an index bare to make explicit that we are talking about a bare charge. And what we mean by this is it may depend on epsilon and it might be divergent. So and then we do what we call renormalization transformation, this bare charge, and I repeat, this is the E that we had so far. This is now called as follows. We split it into a sum like that, and let's give some explicit indices. E renormalized plus delta E. So the bare coupling constant is split into a renormalized coupling constant plus a so-called renormalization constant, such that this object here remains finite in the limit epsilon going to 0, and all the divergences are contained in the delta E. That is of course something that we can do if we have such a formula, because nothing can stop us from doing it. Let me also give a second formula which is then more useful in practice. We can do the same for E square, which is the square of the line before, which is E square renormalized plus 2 E renormalized times delta E. And let's ignore the delta E square. Let's just say plus higher orders, because what we will also assume in this split is that the delta E is of higher orders. All the divergences arise at the one loop level, so they are of higher order compared to tree level. And so therefore we assume that this delta E is of higher order in the perturbation theory than this. And therefore delta E square would be of even higher order and be neglected for today. So let me write here some remarks. So as we discussed, this is by definition, we require it to be finite and epsilon independent. And this will be the new expansion parameter of our perturbation theory. So in a way, we reshuffle our perturbation theory. Before, we might have said we do a perturbative power series expansion in this bare coupling constant, and from now on we will say we do a perturbative power series expansion in the renormalized coupling, and that here is of higher order. And the name of this delta E is so-called renormalization constant. The name constant is a misnomer because it depends on epsilon, but of course it doesn't depend on momentum and so on. So it depends on epsilon and is a power series in the renormalized charge, E renormalized, of order higher order than at least E square. Actually, no. It's even of higher order. It starts at E cube because the vacuum polarization is of order E square. So we split this, and this kind of split is called a renormalization transformation. And in general, you would do that for all parameters in your theory, and here we just consider only one. After doing that, we are at step 2. So we do now renormalized perturbation theory. So we expand in this renormalized coupling constant E up to one loop order, and one loop order for us means up to E renormalized to the fourth power. So for example, for this alpha effective, for all these different experiments, alpha effective I was originally E square divided by Q square plus pi gamma. Okay, and pi gamma is proportional to E square itself. Therefore, if we expand that now up to this order, we get E renormalized square divided by 4 pi. And then we have this E square goes to E square plus 2E renormalized, so plus times 1 plus 2E renormalized times delta E from the E square, which has undergone that replacement. And then we get from the denominator minus E renormalized square A gamma of Q square for the experiment I. Okay. So I've now brought that back into the numerator and replaced pi gamma by E square times A gamma. E square is replaced by E bar square. E bar is then power expanded in the renormalized charge, and terms of order E to the 4 are taken into account, and higher order terms are neglected. So this delta E is of at least of order E square. Therefore that term here is of the order E to the 4th power. Sorry, what has happened here? Divided by E renormalized. Sorry, because I E square becomes E square plus 2 times E delta E. If I factor out E square, then I get that. So that is the same as here divided by E square. So, but this is at least of order E to the 3rd, and that is of the order overall E to the 4th. And if I would plug in here also a delta E, then it would be of higher order than E to the 4th, and so it's negligible. So up to that order, this is exactly the full expression that we have. So, and in general, you would do that for all quantities that you are interested in, and so here we have done that already. Then, step 3, you choose now a concrete scheme for this delta E and for the renormalized E, and that is called renormalization scheme. We choose a renormalization scheme. That is a very crucial step in the procedure of renormalization in practice. So I told you that we know clearly that we can split our bare charge into that way. But how do we split exactly into a finite part and a divergent part? That is not unique, because you can change the divergent part by a finite amount and it remains divergent, and the finite part remains finite. So there is of course an ambiguity here, and fixing that ambiguity amounts to choosing what we call a renormalization scheme. So let me write this in a few different ways, all of which are useful. So choosing the renormalization scheme is equivalent to choosing the split between E renormalized plus delta E. That is also equivalent to saying that you write down a definition of what you mean by delta E as a function of the renormalized E. That is also equivalent to something else, namely once you have defined this, you plug in the definition into this relationship here between, that is now the relationship between your theory input parameter and an observable, right? And so if you plug in some particular choice for the delta E, then you will get a particular version of this formula. If you make a different choice, the formula will look different. So what the definition amounts to is it gives a specific version of the relationship between observables and the theory parameters. changing the theory parameters changes the formula. So it gives a specific relationship between observables and input parameters here E renormalized. If you know what is the relationship between your observables and your renormalized charge, it means you can basically do a measurement and then determine the numerical value of your renormalized charge from the experimental measurement. So it determines the numerical value of the renormalized charge and also the physical meaning of what you mean by your renormalized charge. Your physical meaning and numerical value of E renormalized. All of that is equivalent, and all of that is important in understanding and using such renormalization schemes. And this is the reason why in the literature you find different numerical values for quantities like alpha or other quantities like the W boson mass or a top quark mass and so on, because you can define those quantities according to different renormalization schemes. And if somebody sees a different value for alpha, then it is not a mistake, but it corresponds to a different renormalization scheme, in other words, to a different definition of alpha. Here we will now make a particular choice. We will restrict ourselves to one renormalization scheme, which is very physical and very nice to interpret, which is the so-called on-shell renormalization scheme or on-shell scheme. It's a very famous and very often used scheme. Well, it's not the only one. And this is defined as follows, namely at Q0 square. So therefore on-shell, like the photon mass is 0, so Q square equals 0 corresponds to the on-shell relation for the photon mass. Let us require that at this momentum, we require that the alpha effective at Q square equals 0 is just given by the tree-level relationship E square renormalized divided by 4 pi. That is our requirement. And then we call E renormalized in that scheme is called EOS for on-shell scheme. So that is now the name that we will use. So EOS stands for the renormalized charge according to that specific chosen on-shell renormalization scheme. So it's basically a physical requirement. You require that the renormalized charge basically means the charge that you measure in very low energy experiments, like in this Thomson limit experiment. So therefore for
طبعا بالنسبة لي مصطلح الأونشيل طبعا مصطلح الأونشيل هو المصطلح الذي تكون النسبية الخاصة فيه مفعلة. حسب نظريتي أن النسبية الخاصة طبعا يؤثر عليها أشياء، يعني مثلا نتحدث عن تفاعل، فإنه كلما دخلنا عميقا داخل التفاعل انكسر انكسرت المعادلة E يساوي MC سكوير. طبعا فضاء الأبعاد لن يرضى هذا الأمر، لا يرضى أنه ينكسر، فماذا سيفعل؟ طبعا هتنكسر بماذا؟ تنكسر بماذا؟ أو أقصد لا تنكسر، أقصد معليش، أقصد أن E ستتضخم بناء على تضخم ماذا؟ تضخم C اللي هو السرعة. السرعة ليست ثابتة، إي ستتضخم، وتضخم إي سيغير المعادلة. فبالتالي ما يحصل هو أنه الفضاء الثنائي الأبعاد سيرفض هذا ويجعل تضخم السرعة محسوبا على الكتلة تضعف، أو ممكن نقول الشحنة. وهذا ما يفسر لماذا داخل التفاعل الشحنة تضعف، أو لماذا الشحنة كما ذكر البروفيسور في الرينورماليزيشن نجد أن المقام تتغير يؤثر على الشحنة والشحنة تنقص. طيب ما هي المعادلة التي تفعل ذلك؟ تعالوا نشوفها. هذه المعادلة هي معادلة الطاقة. انظر إلى MC سكوير موجودة في البسط، وانظر إلى R تكعيب، أو انظر إلى M كابيتال موجودة في المقام. عميقا داخل التفاعل فإن M كابيتال ستزيد. يمكن نعوض M بدلالة الطاقة حسب النسبية الخاصة، ليست هناك مشكلة، لأن هناك تناسب في النهاية، هناك تناسب حتى لو كانت التناسب ثابت. التناسب هو ليس ثابت، يعني C سكوير هو ليس ثابت، ليس هناك مشكلة، لكن في النهاية هناك تناسب طردي بين ال M وال E الطاقة. فإن زيادة M يؤدي إلى نقصان E كابيتال الموجودة في الشمال علامة التساوي. والطاقة محفوظة، الطاقة الكلية لأي نظام محفوظ. الأرض طاقتها محفوظة، نحن كلنا نعمل وفق طاقتها هي. لا يمكن الطاقة الأرضية كلها، يعني طاقة كاملة بما فيها الجاذبية وما فيها الحركية، كلها محفوظة. ونحن بناء على ذلك نعمل وفق هذه الطاقة. أكلنا وشرابنا والطاقة التي نستهلكها في الأكل والشراب والمجهود كله بسبب هذه الطاقة المحفوظة. طيب بما أن الطاقة الكلية هي مع طاقة محفوظة، ونجد أن الكتلة بسبب ما زادت، كتلة M كابيتال، فيجب أن يعادل ذلك ماذا؟ MC سكوير أيضا أن تزيد. بالنسبة للفضاء ثنائي الأبعاد لا يهمه ذلك إذا زادت MC سكوير، وبالتالي نجد أن هذه ال MC سكوير ستفوت سرعة الضوء. بالنسبة للفضاء ثنائي الأبعاد يرفض أن السرعة تفوت إلى سرعات عالية، لأن الكتلة تتضخم مع السرعات العالية، فيرفض ذلك. ماذا سيفعل؟ سيحافظ على معادلة الاينشتاين النسبية الخاصة E equal MC سكوير أيضا. طيب كيف يحافظ عليها؟ بما أن سرعة الضوء زادت أو سرعة الجسم زادت بناء على زيادة الجاذبية أو زيادة الكتلة M كابيتال، وهذا الفضاء ثنائي الأبعاد لا يستطيع أن يتدخل فيه، لأنه الكتلة M كابيتال لديها شيء يسمى جاذبية، وهي خارج عن إرادة الفضاء ثنائي الأبعاد. هذه الجاذبية تجعل الجسيمات تنجذب نحو المركز وتسقط بسرعات عالية، فهذا الفضاء ثنائي الأبعاد لا يستطيع أن يفعله. طيب ماذا يفعل؟ يفعل ما هو أعمق من ذلك، وأن يزيد MC سكوير. طيب MC سكوير زادت، ماذا يحصل؟ ستنكسر معادلة أينشتاين بأن السرعة أعلى سرعة هي سرعة الضوء. أيضا هذا الأمر الفضاء ثنائي الأبعاد لا يرفضه تماما، أن يكون أعلى سرعة هي سرعة الضوء. طيب ماذا يحدث؟ بعد ذلك يحدث أنه زيادة السرعة تحسب على الكتلة M small، ويجب على M small أن تنقص. لماذا؟ نقصان M small وزيادة السرعة، إذا وصلت V السرعة إلى سرعة الضوء فنجد أن M small قليلة جدا مثل الضوء. يعني إذا سرعة الضوء، كتلة الضوء مرتبطة بسرعته. لماذا كتلة الضوء عديم الكتلة؟ لأن سرعته أعلى سرعة في الكون. هذه هي النسبية الخاصة، ومعادلتها هذه يعني تثبت هذا الموضوع بالنسبة لأن الفضاء موحد وثابتا ولا ينكسر. والكتلة ام كابيتال لا يستطيع الفضاء ثلاثي الأبعاد أن يتحكم فيها، لكنه يحاربها. فالكتلة ام كابيتال هي دخيلة على الفضاء ثلاثي الأبعاد، فما عليه إلا أن يحاربها. يحاربها بماذا؟ يحاربها بأنها الجسيمات التي تسقط عليها يؤثر في كتلتها لأنها صغيرة. ام كابيتال كتلة كبيرة مثل كتلة الثقب الأسود. ام سمول هي كتلة صغيرة يمكن تكون كيو الشحنة. فهذه الكتلة الصغيرة يستطيع الفضاء ثلاثي الأبعاد أن يتحكم فيها، وأيضا تستطيع الجاذبية تتحكم فيها بالمناسبة. الجاذبية زيادة الطاقة يؤدي إلى نقصان الكتلة، أيضا خاصية أساسية في الجاذبية. هذه خاصية أساسية في الجاذبية. نقصان الكتلة يجي من أين؟ انظر إلى انهيار السوبر نوفا. الانهيار يتم عن طريق ماذا؟ تقليل المسافات، تقليل الأبعاد يعني تغير في الكثافة الكتلية. ثم بعد ذلك يحصل انفجار. الانفجار يعني زيادة نقصان الكتلة، يعني حتى في السوبر نوفا يحصل هذا الأمر. فالجاذبية لديها هذه الخاصية. فإن ام سمول تنقص، وهذا ما يقوله البروفيسور الآن في الرينورماليزيشن. نجد أن عند الطاقات العليا الشحنة تنقص الشحنة بسبب ماذا؟ بسبب أن هذه الآلية التي شرحتها في هذه المعادلة. فهذه المعادلة معادلة كونية ولها كثير من الخصائص التي لم نكتشفها، وأتمنى أن نكتشفها قريبا كلها، لأنها تعطيني معلومات في غاية الغرابة وغاية الدقة بما يحصل في الكون الداخلي، الفضاء الداخلي للتفاعلات، والفضاء الداخلي للجزيئات والذرات، وأيضا في بداية الكون ونهاية الكون أيضا. فهي معادلة جميلة وعميقة جدا جدا. طيب نرجع. طبعا الدالة اللوسية تؤثر بدرجة كبيرة جدا. الدالة اللوسية تؤثر بدرجة كبيرة جدا جدا في هذه الأمور. انظروا إليها فيها علامة سالب. زيادة ام كابيتال تجعل الوضع أسوأ بالمناسبة. لهذا نجد أن تعادل الام كابيتال هي الار موجودة في المقام، وهذه صفة من صفات الفضاء ثلاثي الأبعاد، أن يضخم الفضاء تحت الكتلة ام كابيتال حتى لا تصل ام كابيتال في ما لا نهاية. وهذه خاصية نجدها في سوبر نوفا أيضا. نجد أن عندما تنهار الكتلة فجأة الفضاء يتضخم، والجسيمات تطير من هذا الفضاء الضيق جدا إلى بسرعة عالية جدا، وهو يسمى انفجار السوبر نوفا. فهذه كلها في الدالة اللوسية.
Therefore, for such low energy observables, what that all means is that the prediction of the theory also at higher orders is equal to the tree-level prediction, and then it means that the effective alpha method in such experiments is equal to the theory alpha with no corrections. So step 4, that will now become manifest. So we solve for the renormalization constant. So we have imposed a renormalization condition which fixes our split delta E and E renormalized, but the condition is formulated as a relationship for the renormalized charge, and now we have to solve what does that relationship imply for the delta E. What does it imply? So in the on-shell scheme it means we have to look at step 2. In step 2 we have written down our general observable given in terms of the delta E. When we now require that for q square equals 0 all the loop corrections vanish, then it means that the terms in the round bracket 2 times delta E over E minus the other thing, that must be 0 for q square equals 0. And then we have our condition for delta E, namely 2 delta E divided by E on shell must be equal to E on shell square times A gamma of 0. And then we have an explicit formula for our renormalization constant. And this formula is obviously specific to the chosen renormalization scheme. Step 5. Now we can compute everything. We can compute all quantities that we are interested in, compute all other quantities. And we, in perturbation theory, we go up to order E renormalized, in other words, E on shell, to the 4th power. So and then we can plug in our renormalization condition into step 2. In step 2 we have our formula, but there we had just a simple delta E. Now we know what our simple delta E actually is. Namely, it is A gamma at 0. So we can plug it over there, and then we get the difference of A gamma at Q square minus A gamma at 0. And that was what we called A hat. That was the interesting Q square dependent part of the A gamma, the A hat. That is exactly what remains here now in the prediction. So therefore our step 2 formula becomes alpha effective for experiment I is given by E, now E on shell square divided by 4 pi times 1 minus E on shell square times A hat gamma finite of Q square for the experiment I. And just to remind you, that is the difference of the actual A gamma of Q square minus A gamma at 0. And the A gamma of 0 enters because of our renormalization condition. What has now happened? What has happened is that for all observables, simultaneously the divergences have dropped out. These relationships are infinitely many predictions for infinitely many different observables as a function of the renormalized charge, and all of those infinitely many formulas are all finite. There are no 1 over epsilons anymore. This A hat is a finite formula which we have discussed. It is consists of normal mathematical objects like logarithms and power series expansions in Q square. Therefore, we have absolutely explicit, well-defined expressions in the limit epsilon going to 0. So, all predicted observables are finite. Epsilon going to 0 is possible. So at this point we can remove our regularization and take that limit, and that is what we now do. So we have established the finiteness for all observables. And just to remind you, that is the case for by construction for the first one. So the first observable was the one in this Thomson limit where Q square was 0, and our renormalization condition is constructed such that the Thomson limit observable is automatically finite because there we made our delta E cancel the divergence. The delta E cancelled everything, including the divergence, so therefore this is by construction finite. But for all the other infinitely many observables, it's a non-trivial fact that the finiteness emerges simultaneously. And that is what we discussed yesterday. Yesterday we discussed that we can only hope that it will cancel for all observables, and now we see that it does. So, and as I told you also, higher orders is not only about technical stuff like cancelling divergences, they have now cancelled, but now door is open towards physics discussions, because these formulas contain very interesting and non-trivial predictions for physics, which depend on Q square and which depend on the observable. And so therefore we get now many non-trivial physics predictions. And that is what we want to discuss today as well. Let me just give you a few more comments on renormalization before we actually start discussing physics. What I want to point out is this detail which we have already remarked, which is now important. So why does the whole thing actually work? The point is that the divergence in this vacuum polarization pi gamma of Q square, it turned out to be a momentum independent constant. So the divergence delta was not depending on any Q square, and that is the reason that for all observables, for all Q square, the divergence drops out simultaneously. And
طبعا المومنتوم اندبندنت يعني ما ذكرته أن قيمة المومنتوم لا يمكن أن تكون لا نهائية، لأن المومنتوم فيها الكتلة وفيها السرعة، فمستحيل أن تكون الكتلة لا نهائية والسرعة لا نهائية. لماذا؟ السرعة يعني طاقة، والطاقة اللا نهائية إشكالية بالنسبة للفضاء ثنائي الأبعاد، والكتلة يعني جاذبية، الجاذبية لا نهائية وإشكالية بالنسبة للفضاء ثنائي الأبعاد. يمكن نعتبرها كتلة مطرودة من التفاعل، أيضا لا يمكن أن تكون نهائية لأنه الفضاء ثنائي الأبعاد منتشر في كل مكان، فلا يمكن أن تكون لا نهائية، وأيضا السرعة لا يمكن أن تكون لا نهائية. وهذا ما يجعل أنه النسبية الخاصة يجب أن تطاع، وما يحصل أنه إذا زادت الجاذبية زيادة فإن الكتلة تصغر، أي الكتلة التي تقع تحت تأثير الجاذبية. الثقوب السوداء، الأجسام التي تسقط في الثقوب السوداء، هذه الأجسام لا بد لها، طبعا الثقوب السوداء لديها تسارع كبير جدا، فهذه الأجسام لا بد أن كتلتها أن تصغر، وهذا مدون طبعا في كتاب إن شاء الله في الحلقة 54. فالكتلة لا بد لها أن تصغر حتى تقاوم السرعة الكبيرة، وهذا واضح. السرعة عبارة عن تفاضل أو مشتقة المكان بالنسبة للزمن. إذا كان المكان ضخما والزمن سيكون ضخما، وبالتالي هذا الاشتقاق يكون صغيرا. هذا هو الموضوع. طبعا المكان ضخما، كيف المكان يكون ضخما؟ لأنه كتلة تصغر. يعني اعتبر أن الشمس سقطت داخل ثقب أسود، كتلة الشمس كبيرة جدا، يعني كتلة الشمس تقدر ب نقول أنه 1/10,000 أو 1/100,000 أو قول 1/1,000,000 من كتلة الثقب الأسود. هي كتلة كبيرة جدا بالنسبة للفضاء الذي حول الثقب الأسود، لأن الثقب الأسود زادت كتلته بالشيء اليسير، وهذا سيؤثر مباشرة على الفضاء ثنائي الأبعاد. طيب ماذا يحدث هنا؟ ما يحدث هو أن كتلة الشمس التي سقطت، الذرات الشمسية سواء كان الهيليوم ولا الهيدروجين ولا حتى الذرات الثقيلة مثل الحديد وإلى ذلك، هذه الذرات التي تسقط في الثقب الأسود لابد لها أن تضمحل طيب إذا اضمحلت طبعا سرعتها ستزيد أثناء سقوطها الثقب الأسود، وبالتالي لابد لها أن تضمحل. إذا اضمحلت سيصبح الثقب الأسود ضخما جدا بالنسبة لها، لأن هي ستكون صغيرة جدا والثقب الأسود سيكون ضخما جدا. وهذا ما يقال أنه الثقب الأسود الأبعاد الداخلية ضخمة جدا بالنسبة للأبعاد الخارجية، بسبب هذا أن الكتلة تصغر. طبعا بالنسبة للإنسان يتدمر، وبالنسبة للشمس أيضا تتدمر، لا تسقط كاملة، هي تسقط ذرات. وبالنسبة للذرة تتأين، الذرة تتأين، تخرج المدارات الخارجية ثم التي تليها ثم التي تليها حتى تصبح مجرد بروتون ونيوترون. هذا إذا كان ماذا؟ هذا إذا كان لم نطبق فرضية في الكتاب 48. الفرضية تقول أن جسم الثقب الأسود يقع في بعد يعتبر ربع البعد بين المركز ونصف قطر شوارزشيلد، ربع هذا البعد. إذا كان هذا البعد 10,000 فإن ربعه يساوي كم؟ يعني أفرض أنه النصف القطر 10,000 كيلومتر، فالربع يساوي كم؟ يساوي 7,500 كيلومتر. فسبعة على بعد 7,500 كيلومتر يقع جسم الثقب الأسود، وهو جسم ضخم جدا طبعا، لأنه هو الربع نصف قطر شوارزشيلد، لأنه نصف قطر شوارزشيلد تمتد لحد أفق الحدث، هو يقع في الربع، ربع المسافة، ربع المحيط بالنسبة لأفق الحدث. فهذا هو جسم الثقب الأسود، ليس سنجلارتي، ليس نقطة متفردة موجودة في الفضاء، لا، جسم ضخم جدا موجود في داخل أفق الحدث. طيب ماذا يحدث؟ الشمس سقطت، تسقط والذرات ستحاول أن تضمحل وتتأين إلى أن تصل هذا الجسم وتصطدم به. هذا الصدام يولد موجات جاذبية، موجات الجاذبية تستطيع الخروج من هذا الفضاء، لكنه يستطيع وهي ستكون ضعيفة، ليست ضعيفة شديد، إنما ستكون متوسطة، يعني إذا كان هناك كواكب بالقرب منه ستتدمر. لهذا نجد أن الثقب الأسود موجود في مركز مجرتنا بعيد جدا مننا، يقع على بعد 25,000 كيلومتر، 25,000 سنة ضوئية. أضرب السنة الضوئية في 10 أس 13 كيلومتر على ما أظن، هكذا هذه السنة الضوئية. فهذا هو فالنسبية العامة تنكسر، لكن الفضاء ثنائي الأبعاد يرجع مرة أخرى أو يصيحها مرة أخرى، ولكن يكون محسوب على الكتلة. الطاقة الكلية لأينشتاين تكون محفوظة، E يساوي MC سكوير، لكن زادت C سكوير، السرعة زادت، فإن الكتلة ستنقص.
Let's make that a little bit more explicit. So something which is momentum independent in momentum space, what does that mean in position space or in X space? You go by Fourier transformation from momentum space to X space, and so basically what is the Fourier transformation of a constant? It is a delta function of X. So Fourier transformation of a constant means something local in position space. So that is like a local interaction which can be written as a term in the Lagrangian, and also as a Feynman rule. Let's make that explicit. Our Lagrangian, which initially depends on this bare charge, E bare, can now be written as a Lagrangian which depends on the renormalized charge plus delta E. Let's plug in this distribution, this split, into the Lagrangian. Then we get our Lagrangian, which first of all only depends on the renormalized charge. And then the only place where the charge appears is of course this interaction term, which looks like this: psi bar gamma mu psi times a mu, right? this term. And initially the term appeared with a prefactor minus e times q. And so if you do that replacement, then you get once the same term just proportional to the renormalized charge, and once proportional to minus delta E times the same thing. So that is then the Lagrangian, and I write it here explicitly. The original Lagrangian with a bare charge is given by the same thing where we have the renormalized charge plus this extra term proportional to delta E. And this term gives a Feynman rule. The Feynman rule looks like this. It is the same Feynman rule as we always had, but by convention, such Feynman rules with renormalization constants, they are called counter-term Feynman rules, and they are signified with such a cross here. So anyway, that gives this Feynman rule, and the value of the Feynman rule is minus I delta E times Q times gamma mu. So it's the same as the normal Feynman rule, but with delta E instead of E. And that is a local interaction. Now what happens if I use that Feynman rule in the calculation of processes? Then I get this Feynman diagram that we have computed with the photon vacuum polarization. But I also get now this Feynman diagram here with the counter term Feynman rule at one vertex, plus the other Feynman diagram where the counter term is at the other vertex. I also would get this Feynman diagram with counter terms at both vertices, but they are of higher order and can be neglected. So we need to consider these three Feynman diagrams. They are all of the same order in perturbation theory, because the delta E alone is of the same order as this loop. Therefore, these three diagrams are exactly diagrams of the same perturbative order. And what happens if I add them up? I get exactly this combination that we had, namely 2 times delta E times the usual Feynman diagram, and that gives the 3-level Feynman diagram times the vacuum polarization. So combination, we can write this as the 3-level Feynman diagram times the following correction. So from here we get the correction factor. So let's start here. We get 2 times delta E over E renormalized as a correction factor, because that is just the same as 3-level times that correction. And here we get, let's get the signs correct, we get minus A hat gamma of Q square times E renormalized square. And then you see that is the correction that we get. The A gamma has a divergent part, but the divergence does not depend on Q square. Therefore, the divergence can be cancelled by this constant coming from the new counter term Feynman rule delta E over. And so this is the explanation why this procedure of the renormalization transformation cancelling the divergences, why it works. Namely, it works because the original divergences correspond to local interactions which can be written in terms of Lagrangian terms. And that is the general thing, right? Everything we have done here is, of course, an example. And a general lesson, which is absolutely true in all relativistic quantum field theories, is that indeed the divergences that you encounter at some loop order correspond to such local interactions which can be written as a term in the Lagrangian, and which can be cancelled by introducing such counter-term Feynman rules and such counter-term Lagrangians. And then usually the counter-term Lagrangian and the rest can be combined to such a bare Lagrangian. So let me just write this in general. All quantum field theory divergences can be cancelled in this way. course, I'll refer you again, if you are interested in more details, to the lecture 8 to 12 from 2019. Or to the multi-loop lecture, or if you want even more details. But for us this is sufficient because we have established the general principle and you see that it works and how it works. And this is completely generalizable to much more complicated cases. Do you have questions? Yes? That corresponds to one loop. One loop brings in 2 additional powers of the charge, and therefore one loop diagrams that we consider are of order in the charge. And therefore we do everything consistently up to that order. Yeah, right. I mean, 2 loop would correspond to e to the 6. And if you have a more complicated process with many more particles, then 3 level would correspond to whatever e to the 4 and 1 loop to e to the 6 and so on. So this is adapted to our space.
طبعا هنا ذكر معلومة مهمة جدا، أنه أول لوب هي order of e square، 2 لوب e is 4، و 3 لوب e is 6 مثلا. أول لوب ماذا يعني؟ يعني مثلا أدخلنا في اعتبارنا الفاكيوم expectation value أو كما vacuum energy، وهذا طبعا تعتبر صغيرة لأنه البروتون والكوارك يؤثران في الفاكيوم. الفاكيوم هو يعتبر أنه البير بروتكشن، يعني البير بروتكشن ربما يكون الكترون وبوزيترون يخرجان ويفنيان مع بعضها بعض، يعني قيمة صغيرة جدا هي الفاكيوم انرجي. هذه السكند لوب، يعني الاوردر اوف فاكيوم في السكند لوب، وهذا واضح 10 ايت سكوير، يعني 10 أس ناقص 19 مضروبة في 10 أس ناقص 19 يعطينا 10 أس ناقص 38 إلى حدود الفاكيوم انرجي. طيب ماذا يعني 10 أس ناقص 38؟ هذا يعني أننا نرى الشحنة في 10 بقيمة 10 أس ناقص 38، وهذا يعني أن الفضاء يمنعنا من الرؤية الحقيقية للشحنة، والأمر ينطبق على الكتلة. لهذا نحن الآن في وضعنا الحالي كملاحظين على سطح الأرض نعلم كتلة الشمس، لكن تعالوا نشوف هل البكتيريا ترى كتلة الشمس مثل ما نراها؟ لا. هذه المرة قلبنا الآية، جعلنا الملاحظ هو الصغير في الأبعاد الصغيرة، والمراد قياسه في الأبعاد الكبيرة. فالشمس بعيدة مننا. أضف إلى هذا البعد صغر البكتيريا. إذن هناك بعدين بالنسبة للبكتيريا، اللي هو بعد الشمس من الأرض وبعد الأبعاد أو صغر الأبعاد. صغر الأبعاد تضاف إلى البعد زيادة، فبالتالي هي الشمس تبعد مننا مثلا 150 مليون كيلومتر. أضف إلى ذلك بعد آخر يمكن حسابه بطريقة ما بالنسبة للبكتيريا. إذا البكتيريا كيف ترى الشمس؟ لا ترى الضياء. لا أقصد الضياء، أنا أقصد كتلة الشمس. هل تحس بكتلة الشمس؟ تحس بها ضعيفة جدا، مثل ما نحن نحس بأنه طاقة الفراغ هي طاقة ضعيفة جدا. طيب ماذا عن السكن سير اوردر أو السكن اوردر 10 سي ناقص اللي هو 10 سي ناقص 19 سي 4؟ 38 يعني 10 ناقص 38 زائد 10 ناقص 38 76 أو شيء من هذا القبيل. 76 نعم. طيب 10 ناقص 76 ماذا تمثل هذه؟ شحنة قدرها 10 ناقص 76 بالتأكيد لا نراها، لكن هل هذا يعني أنه لا يوجد جسيمات في هذه المنطقة؟ لا، يوجد جسيمات، يوجد جسيمات مشحونة ولديها كتلة 10 ناقص 76. هذا ما يفترض علينا وحدة الفضاء. وحدة الفضاء يفترض علينا هذا، ويفترض أنه ما دام الفضاء موحد هناك عوالم أخرى كما أنتم الآن عالم في الفضاء، هناك عوالم أخرى صغيرة وهناك عوالم أخرى ضخمة. البكتيريا عبارة عن عوالم، الفيروسات ربما يكون هناك جنس من الفيروسات أقل من البكتيريا، هي برضه عوالم أخرى. الذرات عوالم، الأنوية عوالم موجودة داخل الذرات، البروتونات والنيوترونات عوالم، داخل البروتونات والنيوترونات يوجد الكواركات عبارة عن عوالم أخرى. طيب ماذا يوجد داخل الكواركات؟ يقولون أنها السترينجز، لكن هناك أعتقد أن هناك شيء أكبر من السترينجز يوجد داخل الكواركات، أيضا عوالم أخرى. فالعوالم لا تنتهي، ومع هذا الفضاء كله موحد، كله الفضاء متصل، لكن يظهر الفضاء بهذه الدوال اللوسية. فالبكتيريا ترى الشمس بدالة لوسية، كما أننا نرى الثقب الأسود الموجود في مركز مجرتنا بدالة لوسية، ونرى الكون الخارجي بالدالة لوسية تناقصية. فمن الصعوبة نحن نستشعر مثلا الثقب الأسود إذا كان هناك ثقب أو محور دوران. الكون ككل يدور حول محور واحد، وهذا ما ذكرته في فيديو سابق في هذه السلسلة، والسلسلة السابقة لا أدري، أن الكون كله يدور في محور واحد. طيب هل نحن نرى هذا الدوران؟ هل نشعر به؟ لا، لأنه هناك دالة لوسية بيننا وبين هذا القوة العظيمة جدا. مهما كانت القوة العظيمة أنت بعيد منها، هذا البعد يمثل بدالة لوسية مهما كانت القوة عظيمة. إلا ربنا سبحانه وتعالى لا يتعامل بالدالة اللوسية. خلق كل شيء، أي مخلوق بالدالة اللوسية إلا هو، حتى يتحكم في الكون ويسيطر عليه. هو قريب جدا، أقرب إليه من حبل الوريد، قريب جدا جدا، لكن خلق بقية الكون بالدوال، هذه الدوال اللوسية، حتى لا ينافسها واحد في التحكم في هذا الكون، حتى الثقوب السوداء. هكذا يتصرف الكون، هكذا يتصرف الفضاء.
No, doesn't seem obvious, but there is a deep physical reason behind it. And the deep physical reason is that the divergences come from the fact that the integrals, the loop integrals, go to k equal infinity, and the divergences come from the region where the loop momentum is infinitely large. So they come from regions where we have extremely high energies corresponding to very, very small distances. So the divergences arise from the region in space-time where particles or vertices in Feynman diagram are infinitely close to each other. And that is the reason that they can be cancelled by local terms in the Lagrangian. And in momentum space it's not always a constant, but what always happens is the divergences are polynomials in the momenta of low orders, of certain orders which you can calculate beforehand. And so in this case of the vacuum polarization, it would have been clear from the beginning that the divergence must be a polynomial of 0th order in momentum. But in general, because the divergences arise from infinitely high energies and very small distances in position space, they can always be cancelled by such local terms in the Lagrangian. So that is, as a matter of principle, the intuition which is behind it. And of course, establishing this as a mathematical theorem is far from trivial, but the physical reason is really this. They come from high momentum behavior in the loop and therefore correspondingly to very small distance behavior. Right now. It is also interesting to compare to what we actually know from experiment, because of course our quantum field theory, relativistic quantum field theory with local Lagrangians and so on, is an idealization. We have not experimentally checked what happens at infinitely high energies. Accessible to us are finite energies, very large energies maybe, but not infinite energies. And according to distance scale, we have probed nature at distances up to 10 to the minus 18 meters and so on, or 10 to the minus 20 meters maybe. But we have not probed nature at infinitely small distances. So we do not really know whether nature should be described by an absolutely local relativistic theory up to infinitely small distances, or whether maybe the theory is like that up to 10 to the minus 20 meters, but for smaller distances the physics changes a lot. What this renormalization tells us is that actually physics that we can observe, physics that is experimentally accessible in observables like the ones we have considered, which are defined at least not infinite energies, but at certain energy ranges, low up to a certain maximum energy, those observables are actually insensitive to the physics that goes on at infinitely high energies. Because the regularization and the renormalization procedure basically changes our theory at very, very small distances, and the fact that the limit epsilon going to zero exists means that our observables are actually not depending on the details of how we modify our theory at very, very small distances. And that is very nice, because it tells us that this insensitivity also means that we do not need actually to do experiments at arbitrarily high energies in order to test our theories or to set up our theories. Our theories can be happily defined at certain energy ranges up to the energy scale that we can probe experimentally. And all the higher energies, they are contained in the theory, but actually our predictions are insensitive to those details. This is also a lesson from this renormalization theory, that we have this kind of insensitivity of low energy observables to high energy details of the theory. And I mean, actually you might ask yourself, maybe true nature is described by epsilon equal 0.1. If it were, we would not know, because the limit epsilon going to zero exists. That means our predictions would actually be more or less the same because of the limit. If epsilon is 0 or 0.1 or 0.2 and so on, because the fact that the limit exists means that to a good approximation, everything is independent of epsilon as long as epsilon is small enough. So it tells you that theory could be changed at high energies without us being able to notice. Of course, what I just said ignores the fact that for epsilon going non-zero, we have unphysical things in our theory like d equal 4.1 dimensions. What that means is not so clear, but in principle, I think you get the idea. So therefore, there is a quite physical interpretation of the fact that quantum field theory is renormalizable. It has this connection. We will actually come back to a more physical way of looking at what I've just explained in about 20 minutes. I hope we have enough time today. Otherwise, we will go on Thursday. So let us discuss the physics implications. And let us indeed begin by physics at low energies, where what I just explained plays a role. Let us first look at Q square exactly 0, which is the classical limit or the limit of this Thomson scattering. And what we have achieved by our renormalization scheme is simply the fact that an effective alpha at the Thomson limit, which means Q equals 0, is now predicted to be equal to the on-shell scheme E square divided by 4 pi, because that was our construction renormalization condition. This equality is a definition, and so it simply means that if an experimentalist measures now scattering at these low energies and translates this into an alpha, then our on-shell charge is directly equal to that measured alpha. And so this means that our E on-shell really means physically the charge measured in low energy experiments or in experiments where classical electrodynamics is applicable. And so this alpha in the Thomson limit, or alpha in the on-shell scheme, or E on-shell square divided by 4 pi, that is this famous 1/137 point something. So and you can do extremely precise experiments, of course, in this low energy context. So this alpha here is known to 10-digit accuracy, and therefore this on-shell scheme renormalized charge is also known to 10-digit accuracy. Therefore it's a very, very good and very solid starting point for higher order predictions in QED. Now let us look at the next level. If Q square is only small but not quite 0, such that we take into account the next order correction in a Taylor expansion. So as we said, this blob here can be Taylor expanded in Q square, and for small Q square let us take into account the next order, but only the next order. Then what we get here is this E on-shell square divided by 4 pi times now 1 minus our A hat of gamma, right? Because in the on-shell scheme all that remains is the A hat, this finite remainder of our vacuum polarization, and we have calculated this A hat in the first Taylor expansion, and that was this 1/60, so we get here E on-shell square divided by 60 pi square times Q square over M square. That is now our approximation. What does that mean? That means something very physical, and I really want you to acknowledge this physical interpretation of that result. Actually, let me also write here into the numerator, denominator, 1/Q square. So this is the essential point here of this Feynman diagram. So the 1/Q square comes from the photon propagator. So far we have ignored it, but let us now look not only at these effective alphas in this case, but let us in this case look at the full behavior of the interaction. So the important part of the Feynman diagram is the interaction between the two fermion lines, and the interaction comes from, first of all, the couplings, but then the 1/Q square from the photon propagator, and that 1/Q square now receives this correction. So let us discuss it. And this result contains something that you all know from school, namely the Coulomb potential. Two electric charges attract or repel each other by the Coulomb interaction 1/r square, or the potential is 1/r. And this 1/r is contained in the 1/Q square here. 1/Q square is momentum space, 1/r is position space. but that is the same. So this is really the Coulomb potential here. And that is obviously a correction to the Coulomb potential. That means our QED at one loop order predicts that the QED potential is not 1 over R, but it is different from 1 over R. So let us calculate really the change to the Coulomb potential predicted by QED. And in order to do that, let's really write it as an actual potential in the sense of school physics. You need to know how potentials are related to such momentum space quantum mechanical amplitudes. And that relationship is done in quantum mechanics too, where we did scattering theory. And if you start with a classical potential V of x, the scattering amplitude is the Fourier transformation of the potential, where the argument is the 3-vector Q of the 3 momentum change. And so what we need to do here in order to extract it is the following. Namely, we can Fourier transform back to position space, but replace the 4 momentum by a 3 momentum. So this is a correction to the Coulomb potential. So such a static potential that you know from school or first semester physics corresponds to the Fourier transformation of the propagator at Q0 equals 0. So in the limit of low energies, where you really have charges, the energies of the charges do not really change, only the momentum changes, and therefore the photon doesn't carry away energy, but it only carries away momentum. So let's use the approximation Q0 is 0, and then the 4 momentum square becomes equal to minus the 3 momentum Q vector square. And this is the quantity which appears in quantum mechanics. So then we have essentially the Fourier transform potential, V tilde of Q, is this. So this would effectively be the amplitude for the process happening, and we interpret the amplitude as the Fourier transformed potential. So that is now given like follows: E on shell square divided by Q vector square. So let's remove the 4 pi, they are not important now. E on shell square divided by minus Q square, and then in the bracket we get, or let's do it without bracket, so we have this minus the next term with E on shell to the 4th power divided by 6t pi square, and actually times Q square over Q square drops out, just pi times 1 over m square. So that is now effectively our quantum mechanics 2, the Fourier transform potential, V tilde of Q. It has this first term, which comes from the tree level, and the second term, which comes from the one loop correction. And so we can Fourier transform back V of x So the Fourier transformation of that has been done in quantum mechanics, and this gives 1 over r with the following sign: minus E on shell square divided by 4 pi magnitude of x. So this is literally the Fourier transform of each other. And here we get the Fourier transformation of that. That is a constant in momentum space. So the Fourier transformation is just a delta function with the following prefactor: E on shell to the 4th divided by 60 pi square m square times a 3-dimensional delta function of x. So here you have it. Here you really see the Coulomb potential emerging, and you now interpret that the Coulomb potential 1 over r is directly a reflection of the tree-level photon propagator, which is 1 over q square. Whereas at higher orders, the propagator is effectively modified, and we get here a delta function correction to the Coulomb potential. The delta function is, of course, an approximate result, because we have approximated here our Fourier transformation for small q. for a larger Q, this is not correct, and so therefore we should not regard the delta function as an absolutely exact result. So here small q means large wavelength. The large wavelength cannot really resolve all the fine details around the origin. So for the large wavelength, the corrections just look like a delta function. For smaller wavelengths, the correction will have a more complicated x dependence. But for large wavelengths, the correction just looks like a delta function, which basically simply means that somehow the potential gets stronger at the origin. At the origin, you increase the attractive force. That is what this means. Potential at origin is strengthened. And this has, of course, a very famous application and consequence, namely the so-called lamp shift. Lamp shift is the following. If you have a hydrogen atom, there are two levels. The level 2p1/2 and 2s1/2, where p and s mean the orbital angular momentum is either 0 or 1. And so either from Schrödinger equation and quantum mechanics 1 or from the Dirac equation and quantum mechanics 2, regardless, those two levels are degenerate. So in quantum mechanics 1, you know the levels only depend on 1 over n square for the hydrogen energy levels, 1 over n square, which is 2 here, but they do not depend on L. And that remains true also for the Dirac equation theory. If you calculate hydrogen with Dirac equation, still the energy level does not depend on L, it only depends on n. So these two levels are degenerate according to Schrödinger or Dirac. The hydrogen energy levels, 1 over n square, which is 2 here, but they do not depend on L. And that remains true also for the Dirac equation theory. If you calculate hydrogen with Dirac equation, still the energy level does not depend on L, it only depends on n. So these two levels are degenerate according to Schrödinger or Dirac. But now QED loop corrections predict that the levels will not be degenerate because the potential at the origin is now modified. Which level is affected by the modification of the potential at the origin? Only one of the two levels is affected because the p state has a wave function which vanishes at the origin, therefore it doesn't feel that change. The S wave is maximal at the origin and therefore it feels that modification. And so therefore it is clear that this loop correction will split the two levels and there will be a shift. And this is the lamp shift. Only S state feels the above correction.
طبعا هذا الكلام الذي قاله عن اللو انرجيز يعتبر الاس فيلد او الاس اوربيتال مدار اس. طبعا هذا يختلف من نموذج ذرة الهيدروجين. نموذج ذرة الهيدروجين نجد أن الإلكترون يعبر عنه ب كلما زادت الطاقة يعبر عنها بكلما نقصت المدار، نقص المدار. لكن من ناحية أخرى بنجد أنه مدار L يعبر أيضا عن زيادة الطاقة، وشرحت ذلك في فيديوهات كثيرة، أو زيادة الجهد. نعم، زيادة الجهد مدار L، أو ربما نقصان الجهد. شرحت هذا لأنه يعبر عن الأنجولار مومنتوم. الأنجولار مومنتوم زيادته يعني زيادة الجهد، يعني هناك شيء في ذرة الهيدروجين كأن هناك نوع من التناقض، زيادة جهد نقصان جهد، زيادة طاقة نقصان طاقة، وهكذا. هناك في نوع من التناقض في ذرة الهيدروجين. في الحقيقة كان فسرتها هذه بالثيرمال انرجي للإلكترون، بحيث أن المدارات متقاربة بعض البعض في نهاية المدارات في الذرات عموما. هذه التقارب يعني زيادة الطاقة، وهذه ناتجة من الثيرمال انرجي. شرحت هذا الأمر، لكن أثبت أن مدار L يعبر عن طاقة عالية أيضا، طبعا ليس بقدر مدار L، مدار S، لكن أيضا يعبر عن طاقة عالية بشكل ما.
And therefore we get level splitting. Let me just say, we calculated one Feynman diagram, and this one Feynman diagram shows us that there will be such a level splitting, but it's not the only Feynman diagram. In order to quantitatively evaluate the level splitting, we need all Feynman diagrams, and the other diagrams contribute as well. So the number that you get from here is wrong. It's just not complete, but we get a non-zero result, and this is what we can understand. And as you might know, this lamp shift is extremely famous. It was one of the first applications of QED loop calculations, and it is now still one of the most accurate tests of QED predictions and comparisons with experiment. So this is one of those precision tests of QED. Okay, so how much else can we do today? We only have 3 minutes left, 4 or 5 minutes left. Right, either we can start a new topic or we do more details of that topic. I would say probably, since we had already the discussion of renormalization and low energy versus high energy, let me continue with that point and give you the following remark on so-called effective field theories, which is also a topic of quantum field theory 2, as we discussed in the beginning. And on Thursday I will then do about 20 minutes lecture to discuss the high energy limits. The high energy limit will give rise to so-called running couplings, renormalization group techniques, and so we want to see that as well. But now let us discuss low energies and see the emergence of so-called effective field theories. So basically I use all these physics discussions here also to give you outlooks to important further topics. So let me give you the following remark on effective field theories. And let me immediately drop from the sky the following Lagrangian. Let's say L interaction effective is equal to the following. Let's write here some coupling constant times the following, 1 over m square times f minus 1 over 4 F mu nu D'Alembert F mu nu. So what has happened here? Minus 1 over 4 F mu nu, you know it, that is the kinetic term of the photon. Now I inserted the D'Alembert operator in addition. So overall the dimensionality of this is that is mass square, mass square, mass square. So this is mass to the 6th power. It's a so-called dimension 6 operator. And it has 4 time derivatives. So you should not interpret this in terms of classical Lagrangian dynamics, where 4th time derivatives are very awkward to deal with. But this is only to be used in our expansion of Feynman diagrams and perturbation theory, where the Lagrangian with operators appears in the exponential, in the time-ordered exponential. And there, this creates no problems. It creates a new Feynman rule with a prefactor C6, that is a coefficient. And so the mass square in the denominator accounts for the correct dimensionality of the whole thing. So this gives rise to a new Feynman rule. How does the Feynman rule look like? Let's write it here with a box for this Feynman rule. The Feynman rule contains simply 2 photons. It's a bilinear Feynman rule. There are only 2 field operators in this Lagrangian. Therefore, the Feynman rule corresponds to such a bilinear term with 2 photon lines attached to a vertex. And what is the Feynman rule? I times the coefficient of the 2 photon fields with indices mu nu. And the coefficient is C6 divided by m square times what? So we have lots of derivatives here, and let's do it all by head, and or you can do it at home. So the D'Alembert, of course, gives us the minus q square running into one of the photon fields. So here there flows a momentum q, so the D'Alembert operator gives us minus q square as a prefactor. Then the derivatives inside of that give us a transverse projector that simply reflects the gauge invariance of this f mu. So if you work out the derivatives, you get q square g mu nu minus q mu q nu. This is this transverse projection operator that we have often encountered. And that is the Feynman rule. So the Feynman rule is a polynomial of 4th order in the momentum. And it is transverse. If you compare this to that here, that was basically the same. It was minus I times this transverse projection operator, q square g mu nu minus q mu q nu times the photon vacuum polarization. Right? And this photon vacuum polarization at low energies, so let's say plus these counter terms. So that is then is replaced by just this E square on shell times A hat gamma finite of Q square, and that again for low energies was replaced by Q square divided by M square times 6T pi square. So at low energies, our vacuum polarization can be written like this. The Feynman rule from that new Lagrangian looks like that. That tells us that we can replace our vacuum polarization by the new Feynman rule, or in other words, the vacuum polarization has the form which can be interpreted as a new Feynman rule, where it's exactly the same, Q square times that thing times a prefactor. So we can simply read off that the factor C6 here must now be E square divided by 6T pi square. So effectively, the vacuum polarization is equivalent to the above effective Lagrangian with the value C6 equal to E on shell square divided by 6t pi square. And that makes manifest what I said before. At low energies, such new quantum effects, here in this case, a new effect from a loop diagram, can actually be absorbed or rewritten equivalently just as a new Lagrangian. And the new Lagrangian is again local because we are working at low energies, and therefore compared to our low energies, the loop momenta are very large, and therefore this Feynman diagram effectively corresponds to a local interaction where these two vertices are effectively at the same space-time point. Therefore, that can be and that makes manifest what I said before. At low energies, such new quantum effects, here in this case, a new effect from a loop diagram, can actually be absorbed or rewritten equivalently just as a new Lagrangian. And the new Lagrangian is again local because we are working at low energies, and therefore compared to our low energies, the loop momenta are very large, and therefore this Feynman diagram effectively corresponds to a local interaction where these two vertices are effectively at the same space-time point. Therefore, that can be written as an approximation like this. So this is general, and so let me write down the moral of the story. Then we stop. So at low energies, new effects are often equivalent to new terms in the Lagrangian, and that is what is called effective field theory. And what the loop calculation simply does in that context is it gives us the value of the coefficient C6, and once the loop calculation has given us the value of the coefficient C6, we can completely forget about loops, and instead of loops we just use that Lagrangian, which is a simple Lagrangian with a simple Feynman rule, and it will give us the same physics as the physics of the vacuum polarization. So then the entire physics discussion possible using this effective theory Lagrangian. And in this context, it becomes possible to easily, for example, calculate corrections to atomic levels, because then you simply have a new Lagrangian. You could convert it into a quantum mechanical Hamiltonian, and then you can maybe do quantum mechanics 1, just where you have an effective new term of the Hamiltonian, which looks like this, or which comes from that. And that effective new term in your quantum mechanics 1 Hamiltonian is known to give the same physical effect as the loop correction in QED. So that is, of course, a very powerful possibility. And one can say much more to this, but this is maybe now an outlook to a topic which will be the content of next semester's lectures. Okay, so let us stop here and you with the lecture for about 20 minutes. It is less than 1 page, so that should not take more than 20 minutes. And let us finish our semester on quantum field theory 1 with a remark on physics at high energies. So again, restricting ourselves to this kind of observables in QED, where we look at E plus E minus scattering, for example, and we only look at corrections from loop graphs involving the photon vacuum polarization. And let's, for example, look at very high values of the photon momentum Q square, for example, equal to the Z boson mass square, which is very high compared to QED energy scales, or even higher scales like the grand unification scale or we could also go to infinity and ask, how does the QED prediction behave for very high energies of the photon? So then we are looking at very high values of the photon momentum q square, for example, equal to the Z boson mass square, which is very high compared to QED energy scales, or even higher scales like the grand unification scale, or we could also go to infinity and ask, how does the QED prediction behave for very high energies of the photon? So then we are looking at these kinds of diagrams. That is our approximation, that we only look at photon vacuum polarization corrections. And all of those can be absorbed or parametrized in terms of such an effective alpha. And the effective alpha is then given in our on-shell renormalization scheme as E square over 4 pi in the on-shell scheme, divided by 1 plus the loop correction. 1 plus E square divided by 12 pi square times the logarithm of m square divided by minus q square. Okay, and here I have inserted two things. First of all, I have inserted the on-shell renormalization scheme. In the on-shell renormalization scheme, our vacuum polarization is modified by that counter term delta E, which had a specific value, and it led to replacing the mu square from the calculation by the electron mass square here. And the second thing I did is inserting the approximation for high energies, where there was a logarithmically enhanced term proportional to log q square, and I neglect all the other terms which are not enhanced by log q square. So log q square goes to infinity, and so let us neglect everything which doesn't go to infinity. Then this is our approximate result, and therefore indeed the main feature is that we have a logarithmic increase. And as I already explained to you, this is a typical thing, that at high energies in quantum field theory, the theory predicts such logarithmic increases in the energy scales of the problem. And here we see it, it appears in the denominator, of course, but anyway, it is a logarithmically increasing effect which corrects here the tree-level prediction. The tree-level prediction would be effectively a constant, but because of that higher order loop correction, the cross-section and the effective interaction strength is not constant, but it depends on the energy in a logarithmically increasing way. So, and is the effect of that logarithmic increase actually positive or negative? So does the effective interaction strength decrease or increase as the energy gets higher and higher? So that is right, this is the effective interaction strength by which the two fermions here interact. The higher that value is, the higher the effective interaction strength is. So when q square increases, we get here a negative logarithmic term. The negative logarithmic term appears in the denominator, therefore overall the whole thing increases if the energy q square increases. So the effective interaction strength becomes stronger and stronger. Let's write it down. Becomes stronger at high energies, which are of course equivalent to high momenta, high scattering momenta, and that is also equivalent to very small distances. So you probe smaller and smaller distances, basically the two fermions get closer and closer to each other, and by getting closer and closer they feel a stronger interaction than you would expect from classical electrodynamics. So the interaction strength gets stronger as the typical 1/r potential. So let's look at some numbers. So for example, if this minus q square is equal to the z boson mass square, then I wrote on here some exemplary numbers. So the logarithm is then essentially the logarithm of what? Electron mass square, which is 5 times 10 to the minus 4 GeV, and the Z mass is around, how do you know what the Z mass is? Yeah, 91 GeV, so let's say approximately 100 GeV, and then you have here, and that whole thing is squared, 10 to the minus 4 divided by 10 to the 2 is approximately 10 to the minus 6 times 5 square, and the log of this gives about minus 2.5. So this is this correction, minus 2.5. And comparing this or multiplying this with that number, minus 2.5 times that, this is around 1% times 2.5, so we get a few percent correction of the effective interaction strength. So interactions between charged particles at energy scales of the Z boson mass, like we have at high energy colliders, is a few percent stronger than you would expect by classical electrodynamics. Few percent is a large effect for the precision that we have at particle physics experiments, and therefore I write it is a large effect. What happens if minus q square is equal to the grand unification scale? Do you know what the grand unification scale is of this hypothetical grand unification? Which is of course a theoretical idea where all the forces could become equal. That is around 10 to the 15 or 10 to the 16 GeV square, so it's about 12 orders or 14 orders of magnitude larger than the energies we have in experiments, so it's currently not accessible by experiments in particle physics. But anyway, then the logarithm would be of course accordingly larger. Then we would have here the electron mass divided by 10 to the 16 square, and that is around minus 80. If I did the calculation correctly, it's just approximate. So if you have here minus 80 and here around 1 over 100, you get an essentially 100% effect, a very large effect, and so very large effect. So and this shows you, so the electromagnetic interaction gets 100% corrections, so, or it could also blow up. The denominator could conceivably even go to 0. So anyway, the denominator can become really small, and therefore we get very large corrections to the effective interaction strength. And that shows you that it's at least plausible that at this energy scale, the electromagnetic interaction becomes equally strong as the strong interaction. And that is exactly the point of grand unification.
سبحان الله سبحان الله سبحان الله تعالى سبحان الله. هذه معلومة في غاية الجمال، في غاية الجمال أن على الإلكترومagnetic سترونج تكون بقوة الجراند يونيفيكيشن، وهذا ما توصلت إليه في كتابي. شيء غريب جدا يعني، أنه المجال المغناطيسي قوي جدا بين الفيرميونات، قوي جدا جدا. شيء غريب جدا أن يتفق معي. أنا طبعا هذه الحدود أو هذا الكلام لم أصله في المسح السابق، فهذا بالنسبة لي جديد يعني، أنه الجراند أن عند الأبعاد الصغيرة جدا فإن القوى الكهرومغناطيسية تتضخم، وهذا ما توصلت إليه في كتابي. وذكر أنه يساوي القوى الكهرومغناطيسية تساوي الجراند يونيفيكيشن. ففي القوى الكهرومغناطيسية ما الذي هو يكون أقوى من الآخر؟ القوى الكهرومغناطيسية عبارة عن اثنين، مجال كهربائي ومجال مغناطيسي. ما هو الأقوى؟ المجال المغناطيسي. المجال المغناطيسي أقوى من المجال الكهربائي. المجال الكهربائي يتحدث عن شحنة تطلق هذا المجال. المجال المغناطيسي يتحدث عن شحنة وحركة. من معادلة لورنز نجد أن المجال المغناطيسي يتحدث عن شحنة وحركة. فهذه الشحنة والحركة هذه الحركة اللي هي السرعة تجعل المجال المغناطيسي يفوق المجال الكهربائي، لأن السرعات يمكن تصل مراحل بعيدة جدا، وبالتالي نجد أن الحركة مربوطة بالمجال المغناطيسي. وبما أن الطاقة عالية تحت في الكواركات فإن المجال المغناطيسي يلعب دورا كبيرا، وهذا ما توصلت إليه في كتابي، أن المجال المغناطيسي يلعب دورا كبير لدرجة أنه يساوي القوة النووية القوية، وهذا ما ذكره البروفيسور. يعني هذا اتفاق في غاية الغرابة وغاية الندرة. إنه القوة النووية القوية ما هي إلا قوة هو ما هي إلا مجال مغناطيسي، والقولونات ما هي إلا مجالات مغناطيسية. شيء غريب جدا، يعني شيء غريب جدا، شيء مدعاة للفخر. ما سأفعله هو أنني سأسجل هذه الحلقة في قسم آخر وسأنشرها لوحدها هذا الكلام، لأنه يتفق تماما مع نظريتي وتجعل النموذج تجعل نظرية حلت الأمر نهائيا، حلت الموضوع كله. فشيء غريب جدا جدا يحصل في هذا الموضوع. سبحان الله.
All forces could become equally strong at such energy scales. And this is how we know what the grand unification scale should be. If grand unification exists, then it should be an energy scale where the effective interaction strengths of all forces are approximately equal. And here we see that we can actually calculate the effective interaction strengths at different energies, and in that way we can obtain information on this hypothetical grand unification scale. Let me just give you also the full calculation, including all fermions, not only the electron but all leptons and also the quarks, which are also strongly interacting. Then the effective alpha at the scale q square is mz square is approximately 1/128, and so this is really a 6% effect. So that is the true result if you do the exact computation or the best determination which is currently feasible. Then you see that you really can define, and you can then do a very precise definition of that without approximate equal signs but with exact equality signs, and you will see that this effective alpha has about this value, which is 6% bigger than the value determined in atomic physics experiments. Yes. Because the ZMAR scale is a very useful reference scale for electroweak scales, you could just as well choose the W boson mass or the Higgs boson mass or the top quark mass, or simply say 100 GeV as an energy scale. But the ZMass is the most precisely known numbers out of all the numbers I mentioned. Therefore, if you choose any scale, then why not the ZMass? But it's just a reference scale for a typical energy of the order of electroweak interactions. Right. Okay, so let's just finish by a few comments. As I already said, this logarithm of E over m enhancement is typical for quantum field theory predictions at high energies. And there is a physical observable relationship between the effective interaction strengths at low energies and the effective interaction strengths at high energies, and quantum field theory predicts what that relationship will be, and it is of course experimentally measurable, and in that way we can confirm this loop prediction of quantum field theory. Confirms the loop predictions experimentally. And now the final remark is about an outlook to a very famous theoretical framework in quantum field theory. Namely, what you see here is that you can parameterize and absorb such important loop corrections in terms of effective interaction strengths. And that gives rise to the concept of running coupling constants, and then in terms of those running coupling constants, there exists a theory called renormalization group theory, where you can immediately predict the running, in other words, the energy dependence of such running couplings, and therefore of the physical effective interaction strengths of processes. So let's write that down. This can be absorbed by defining a different renormalization scheme. Namely, we can use, instead of this on-shell renormalization scheme, we can use a scheme where we might use a renormalized coupling, which is E effective at Q square, let's say, instead of this E on-shell that we had so far. The point of choosing a renormalization scheme was always twofold. We need to give a definition of the split of the bare coupling into a renormalized coupling and a renormalization constant, and how we shift around finite parts is up to us, and how we split it then affects the relationship between the renormalized coupling and observable quantities. For the on-shell scheme that we have chosen, the result was that the on-shell coupling agrees with the effective alpha measured in the Thomson limit. And now we can instead use a new scheme where the renormalized coupling agrees with the effective alpha at some momentum Q square. A very natural generalization of the whole thing, and then we have such a running coupling. In general, running couplings, and they are governed by the renormalization group. Because the difference between such a scheme and the on-shell scheme is that this is now kind of a family of schemes, because for each value of Q square you have a different renormalization scheme. So in some sense this is an infinite set of different renormalization schemes for depending on Q square. And how the different E effectives for the different Q squares are related to each other, that is predicted by the renormalization group. So the renormalization group gives you a renormalization group equation, which tells you something about the derivative of that with respect to Q square. So you get a differential equation, you can solve the differential equation and then predict the running of the coupling as a function of Q square. That is of course an outlook to quantum field theory 2. But actually I'm not completely sure whether we will do it because it's already completely on video. Namely, these are the videos, I think video 19 to maybe 18 to 20 from 2019 and 20. So it's 3 videos on exactly that topic, which essentially covers it completely. Okay, this was my final remark. With this, let me thank you for your attention and really the very nice active participation in all of this semester. I hope it was kind of interesting for you as well. We had now this introduction to quantum field theory with a strong emphasis on free field quantization for a spin different from zero, and then with lots of applications and examples in quantum electrodynamics. And if you are interested, I will be happy to see you also in some of the lectures and seminars next semester, where we will take you to the next level if you want. Okay, so thanks a lot, and then let's do the exercise.
هنا طبعا نحن أيضا نكون انتهينا من السلسلة الأولى نظرية المجال الكمي، وبعد ذلك تبقت لنا السلسلتين أو 3. السلسلة القادمة إن شاء الله ستكون 15 أو 18 فيديو سنحللها كما حللنا هذه السلسلة، والسلسلة بعديها ستكون 12 فيديو. السلسلة بعديها هي الستاندر موديل ذات نفسه، ستاندر موديل، والسلسلة القادمة هي التكملة للQED 2 اللي هو سنأخذ فيه الباث انتجرال وما إلى ذلك، والبعدية الستاندر موديل. بعد ذلك أكون قد انتهيت وسأبحث عن سلسلة أخرى. هناك سلسلة مالتي لوبس أنا شايفها في غاية الأهمية، لكن هذه ستكون سلسلة قائمة بذاتها، لن تكون ضمن هذه السلسلة التي عنوانها نظرية علي يوسف تفسر الستاندر موديل. ستكون سلسلة قائمة بذاتها تتحدث عن المالتي لوب بإذن الله تعالى. الآن لدينا سلسلتين إن شاء الله سنغطيها في نفس السلسلة هذه. في نفس السلسلة هذه سيكون عندنا سلسلتين 18 فيديو و12 فيديو، مجموعهما يعني 15 فيديو و12 فيديو، مجموعة 27 فيديو بإذن الله تعالى. سنواصل في هذه السلسلة مباشرة بإذن الله تعالى. السلام عليكم ورحمة الله.